You got it.
I think it's a
Video.
sorry for that. Okay, sorry for the delay. I just quick feedback. I just explained. Here we have rbr. It's a manufacturing of oceanographic instrument with high accuracy for application for engineer, researcher, or people who like to high performance measurement for the seawater, the fresh water, and we provided several different family equipment from sensor, logger, system, on OEM. The sensor, it's just to take some measurement for the pressure, the temperature, oxygen. We don't have memory, don't have a power for that. If you would like to have a logger to store the data, it's possible to move on a compact logger or a standard logger for the two different family coming from rbr. And we have energy plus battery plus electronic to store the data. And after we have the system with a modem inductive, it's provided data from the sea bottom to the surface on connecting on the buoy with a telemetry system, including Iridium on GSM, data communication over the world. On to finish, we have the last family for the OEM product. It's a very specific application coming from, for example, for the rbr-Argo, for the Argo float, or rbr-Legato for to providing a IUV or glider. It's very, very specific and need a specific request on collaboration with rbr for that. Here we have a large range of equipment coming from rbr with the sensor, just with the connector here. After we have the small logger with one parameter, and after we move for the other, we move for the to the 2 channel on 5 on 10, moving to the concerto to the maestro with a large multi-parameter sensor with a large CTD. Here we have a large family product coming from rbr. It's with a solo, with a compact logger. We have the standard logger with the concerto, maestro. After we have the sensor here, and we have all the large integration sensor with CTD plus, for example, here T audio on a turbidity sensor for 5-channel acquisition. Here we have a system with a modem inductive. And after we have the specific measurement for very high pressure, for the high accuracy pressure measurement with the line product coming from the quartz. It's a BPR quartz Q or rbr quartz Q for the shallow water. On the deep water, we have the rbr quartz Q plus. It depending what you want to do. After we have all the product line. Whoa. After we have the product line coming with a canister, battery canister to update your time deployment with a large battery. On the Cervelo for the telemetry with the GSM or Iridium modem. To finish, we have the DMO wire worker. We have a specific collaboration with this company to providing provider with mounting with the CTD on the CTD++, for example, chlorophyll, oxygen, turbidity, to free flow acquisition on the water column with the telemetry connecting to the server. It's a very, very interesting product on collaboration with rbr. Today, the main topic for the study of CAIO, it's about the rbr Solo D. It's a very compact logger, just with cell contained memory on one battery, one cell A battery. And we have two different range possible for this type of sensor. Logger, we have the 0 to 1000 D bar. It's a plastic housing on a specific plastic, plus and after we move for the depths, solo depths, and it's for titanium housing for 10,000 D bar maximum. We are providing high accuracy and higher resolution for this type of sensor. And if you have a possibility to have some different sampling range, and it's depending on the sampling range, provided you different day deployment on Mac, and you have some large reading data with this one single battery AA. For example, at 1 Hertz, you have average 400 days deployment for 44 million reading data. It's very, very large. And if you sampling at 5 second sampling, you have average little less 5 years years deployment. It's very long deployment for 42 million reading data with one single battery. For the compact longer, we have, I explained, we have the shallow water deployment for the specific housing in plastic, in the yellow plastic, 0 to 100 meters with 0 to 2 Hertz sampling. And after, you have possibility to update this option of the acquisition with a fast 8 or 16 to 32 Hertz for the shallow sampling. And you have other configuration with D tide and D wave for the specific measurement around 0 to 15 meters depth with a specific wave averaging on burst mode to do some measurement for wave. After, you have the second family product with a depth, Solo D depth, deep, for maximum 10,000 meters depth. And it's housing, it's different because it's a titanium housing, more robust for deeper application. But we have the same option for the sampling range, the 0 to 2 Hertz. And after, we have possibility to move for fast 8, 16, or 38, depending what you want to do. And after, we have the possibility to mix with D with temperature to add coming for not solo, but rbr duet TD, T for temperature, D for depth. And we have two options for T with a standard and fast acquisition, depending. And we have the D rbr duet D TD standard, and we have the depth with the titanium housing for the same than the solo on the duet for the shallow water and deep water. We have the same product, similar product. The Solo D, it's a very easy equipment to use. It's only use one battery, and you have a canister. When you open your yellow canister or the gray titanium canister, we have access directly to the inside equipment with a battery pack, with a battery here in this Here we have the second. On here we have the memory on the acquisition system. It's very, very easy for you to change a battery. You have possibility to use a cells battery with lithium or alkaline, or depending what you want to do, what you have. It's very easy to change the desiccant tool. You have that on the support kit provided with the equipment. To connect your logger to your computer, you have a connector coming here with a sensor. It's a USB-C connector, and you have the cable providing for that with a USB-C and USB-A to connect to your computer. Very, very, very easy. And after we have a software, it's coming, it's Ruskin. And for that, you have a connection directly with a software display, and you have possibility to check the configuration of the system. You have possibility to check the configuration of the system and to change the sampling range and schedules your time deployment, the date of the start, and you have the possibility to have the end of the deployment too, on the choice of the battery. I will show you that just after. I will just explain you the difference between the two family products, between compact and standard. Today we are speaking about solo and the compact, the compact logger. We have two possibilities with a compact. We have the solo, which just only use one battery. On the duet, it's the same, but two parameter acquisition. TD for temperature and pressure, D only for the pressure. It's very easy equipment, very small, if you have a size critical for deployment, it's very easy to deploy. But if you would like to have more long deployment, it will be possible to move for the standard logger. The main difference coming with the battery and the memory. On the name, it's for the solo here, we move to the Virtuoso D with all the same option. And for the Duet TD, we have the same. And to compare, we have the Duo TD with all the same option with a fast acquisition, wave, and tide. Here we have a table with a comparison between the two different sensors. One is a compact, other is a standard. What I explained you, it's you have just one battery AA. Here for the standard, we have the 8 battery. The memory, it's more increased for the Virtuoso to 2,200 for memory readings. For the depth range, we have the same for the shallow and deep deployment, deep range. For the solo, we don't have option for activation or communication. For the Virtuoso or for the standard, you have possibility to have in standard. We provided the twist activation just when you're at the C deployment, you turn the system on its run. You have a vibration on your horn. You say, okay, it's run on. You can put at the C. You have possibility to change end cap with an external connector, for example, for the RS32 communication link, and to add a power for a long-time deployment or to real-time acquisition data. For the autonomous deployment, we have access to Wi-Fi. It's available. It's very easy for example, when you do some profiling in a small vessel, we don't have a possibility to open at sea because you have a risk about the sea on the logger. You just use the Wi-Fi, very easy to use with your phone and application is available for that. For the compact and standard, we have provided the same accuracy, the same resolution, but high accuracy and high resolution. For example, about deployment, here we have three examples. One example, it's in continuous mode at 1 Hertz. It's around the same, it's just different between 20 days, but it's around 1 year. But after, for example, at continuous mode at 16 Hertz, it's 44 days deployment for the solo, on 19.5 days for the standard. On here, the limit, it's a battery. On here, the limit, it's a memory. It's very different. Yeah. And we have this in the example 3, don't have access for the solo, but we have access with the mode burst in 1 month with the standard logger. I would just like to explain the utilities of Ruskin. Ruskin, it's a software provided with all the sensor and logger coming from rbr. And now it's possible to use Ruskin to configure and to prepare your deployment. For example, you have possibility to simulate an instrument. Here I simulate you click to simulate an instrument. After you arrive on new display where you have the compact instrument, and you choose, for example, the rbr duet TD, and you have option for the acquisition sampling. Here we have the standard zero. In the standard, it's 2 Hertz. After we have possibility to move fast 8 or 16 or more, depending what you want to do. And after you just click OK, and you arrive on new display where you have access to the planning tools for the prepare your deployment. Here we have access to the sampling, for example, 1 Hertz. You have access to the battery to choose your battery, and after you have access to the schedule for your deployment. For example, now I would just to check my sampling range. Okay, I move to 1 Hertz, perfect. It's coming for 57 days time deployment, it's okay. With the battery, you have access here to the battery. You use a lithium channel chloride for that. And if you change battery here, we remove for alkaline, for example, you have a new display and you have a new new calculation and you have a new time deployment per year. It's 70 days before it's more 15 days. We have a difference coming from the battery, in fact. I think it's the main discussion for that today. I just would like to upcoming webinar on today with Steph Stimson in Australia. We have a large Ping the President webinar with Ping the President with rbr about rbr instrumentation with Greg, the President of rbr, will be presented with Steph 1 hour presentation about different solution products on they are looking about new question about instrumentation coming from rbr. Thank you for your thank you for that. And now I will be presented to share my screen and to present it to Kayo for the second part of this webinar.
Hello, everyone. Can you hear me?
Yes.
Awesome. Just gonna start my presentation. Can you guys confirm that you see my presentation?
Yeah, it's okay.
Okay, perfect. My name is Caio Stringari. I am based now in France, doing my postdoc here with France Energy Marines. However, this talk is going to be about my PhD that I did at the University of Newcastle in Australia, where I was supervised by Dr. Hannah Power. And the talk today is about pressure sensors in the age of artificial intelligence. So I'm going to talk a little bit how I use artificial intelligence techniques to extract data from the RBR sensors and to study surf and large language processes. Um, so in this talk, I'll be talking mostly about how I managed to do that. And I'm going to give 3 examples of how and why would you do that. And those examples are time series classification, a wave by wave classification. So look at individual waves in the record, and a little bit of unsupervised. I'm going to explain what that means in a bit. Data exploration. So how you can use machine learning and deep learning to actually explore the data in just for the features in your data and try to get a feeling of what's going on if you have a lot of data. So just a little bit of definition here. Artificial intelligence and machine learning. So machine learning is a branch of artificial intelligence. Artificial intelligence is a more of a global concept, and machine learning focuses on developing programs that actually learn from data. So in general, when we talk about machine learning and artificial intelligence, we're talking about learning from data. So we have the data and we try to learn from that. However, in reality, as the comics here illustrate, machine learning is about linear algebra. Uh, there's a lot of math involved in the process. There are a lot of tools today that actually abstract that, and you don't have to worry about the math too much. But in the end, it's about data and use maths, in this case, linear algebra, to get your answer. And as the comics illustrate here, you can get wrong answers as well. So you have to be aware of what you're doing, and if your input data looks okay, and if your output looks okay. So it's not that simple. So most of the time you're doing data cleaning and making sure that your data actually looks okay. So there are different types of machine learning. There's the classical machine learning that are the techniques developed in the 80s and the 70s that are clustering, linear regression from the 1800s. So we're learning from data in those techniques, but they are older techniques and they refer usually as classical machine learning. And more currently, we have neural networks and deep learning and ensembles. So ensembles refer to decision trees. If your data are simple, you have not much data and you have fairly clear features in your data, you can go with classical machine learning. However, if you have complicated data and lots of data, and you have to be sure that you have something very accurate and precise, you probably will be thinking about using ensembles and neural networks and deep learning. So what I'm going to be talking about here in my talk today is about supervised learning and unsupervised learning. So I'm going to give examples of those both of those types of machine learning. So supervised learning, you know the labels. So 2 examples of the task are classification and regression. So you have your input data and you have your label. So you know both the input and the output. And your goal is to get a model that describes the output, knowing the inputs. For unsupervised learning, you don't know the labels. So you just have the data and you're trying to extract something from that data that you can make sense of. And the best known example of unsupervised learning is clustering. So you have a bunch of data points and you're trying to cluster them together and see how they relate to each other. Um, However, the first thing we have to do is actually to collect the data. And for this example, we're collecting data in the surf zone, so in the near shore. And the nearshore has different divisions. So for example, here we have the outer surf zone where the waves start to break and start to propagate towards shore. And then you have the swash zone, so where the waves go up and down the beach, and you have that area in the beach that is either wet or dry depending on the motion of the waves. And this talk would mostly be focused in the inner region of the surf zone and in the swash zone. So very, very near shore, like right in the boundary between the wet and dry beach. So to collect data, our standard procedure there in Australia was to have a chain and to have the pressure sensors attached to the chain with cable ties and tape. And we stretch the chain the cross-shore direction here. So we start at the swash zone and we stretch the chain all the way down to ideally to the offshore here, to the outside of the main breaker. And in the chain, we have the pressure transducers attached to the chain here. So we have several pressure transducers, so we can have we can log the surf zone and the swash zone fairly robustly. And we also measure the beach profile using standard total stations and GPSs. And for example, here we have a view and a cut view of where the pressure transducers would be deployed for this beach in particular. We also record video data, so we can combine the pressure transducer data with the video data. And I'm going to talk a little bit more about that in the next slides. And during my PhD, I was kind of lucky to go around pretty much the entire coast of New South Wales and a bit of Queensland doing this deployment. So we do the same deployment here for different beaches, and in the end see how they compare. And just in the top corner here, just to zoom in how the rbr solo looks like, and I'll zoom into the chain. It's a fairly simple setup, and it's very, very efficient. So I'm going to go right into the first example here of application of machine learning to pressure transducer data. And the first example is how to define a model to actually classify the time series you're recording, because you're recording time series in different locations in the surf zone and in the swash zone. So the first task I had to do in my example, but it could be relevant to any other example, is to actually classify the time series to know where in the surf zone or in the swash zone I am. So we have two very different examples here of time series. One is from the surf zone. So we have the waves fairly frequent here, and it's about 2 meters deep. On the other hand, we have the swash zone here, and the waves are a lot more rare, and it's very shallow. So it actually bottoms out here. So it's dry for a period. For a human observer, you can clearly tell the difference between those two time series. They're very, very different. But if you have hundreds of thousands of time series like that, it gets time consuming. So it's really time consuming to actually classify those time series manually. So what I did was to train a model to actually classify the time series for me. And the input to the model is a time series, and the output is a label. So in this case, I used a Ensemble model, which is a decision tree. And more or less how it works, it's not exactly how it works. So it looks at features in the data. For example, in this case, it looks for the depth, if the depth is less than 0.1 meter, and the period is less than 10 seconds, it would be a surf zone time series. On the other hand, it would be a swash zone time series. So I can very quickly, once I have the model, classify different time series. So if I have hundreds of thousands of time series, a model like this takes a few seconds on the relatively cheap computer to classify the time series, and you get really good accuracy. So on the right side here, I have the results for this specific model, and it classifies the time series with pretty much 90% of accuracy. So it saves a lot of time if you're doing data management, which when you have a time limit budget, for them doing a PhD, it actually helps quite a lot. More on the science side now, one thing I did during my PhD, we had this question about how many broken waves we have in the surf zone. So how many, given a time period, how many waves are broken and how many waves are not broken in the surf zone? And to answer this question, one, we needed to know when the waves are breaking. And second, we need to have information about those waves. So from the video information, we get when the waves are breaking. So because we can actually see in the video when the waves are breaking. And from the pressure transducer, we get the actual information about the wave. So the wave shape, the wave height, and wave period, and so on. So we combine here the video. So we extract this cross section here from the video. Every frame in the video, we stack that in time. So in this axis here, we have time. And in the y-axis here, we have cross-shore distance. We track the waves in this diagram here. So each colored line here is a wave. And we know in the cross-shore position where the pressure transducer, the pressure sensor is. And then we can correlate directly where the wave breaking happens to which wave in the record we have that. It works fairly well. However, one, it's time consuming because you need to align all the waves perfectly here. And two, you not always have a camera, or it rains and your data is corrupted. Like you don't have the camera data. So if you think you have hundreds of thousands of time series and hundreds of thousands of waves and only a little bit of camera information that you can actually tell when the waves are breaking, you can again use machine learning and build a model to actually help you to do that more quickly, more efficiently. And the way I did it, you could do that different ways. You extract one, individual waves from the pressure head record. In this case here, we're using a local minimum analysis. So we're looking for the troughs here in the record. So in the first graph here, you have time in the axis and pretty much depth here in the y-axis. So we're looking for the troughs in the record here and the crests, and we are isolating individual waves. And for each individual wave in panel B here, we extract features. So for example, we extract the wave height, we extract the period, we extract as parameters A and B here. So it's the distance from this point to this point to the crest is the A parameter, the B parameter is what is left in here in time. We extract the trough depths here, the heights of the crest, and so on. We can extract lots of parameters from one single wave. And once we know those parameters and from the video record, we know whether that wave is broken or not broken, we can actually develop a machine learning model where your inputs are your wave features, so the information you extract from the waves, and your output is either a label that tells you if the wave is broken or unbroken from the video record. So you develop this deep neural network here. Oops. And then you classify the waves. And once you train your model, so once your model has seen enough data, you can apply that model to new data that's unlabeled, the data that you don't have the video, and you can build very, very robust data sets on that way because you have a lot of data, classified data. In this example, the classification accuracy of the neural network is about 15%. It's not state-of-the-art result, but it's a fairly good result because it's a fairly complex problem. And we could use this data to actually answer how the probability of wave breaking or the fraction of broken waves vary across the surf zone. So the question we were interested in was, what's the probability of wave breaking across the surf zone? So for example, in this graph here, we have in the x-axis, we have the depth, and the y-axis here, we have the probability of wave breaking. So by classifying the waves with the neural network and knowing the total number of waves and the number of waves that were broken, we could get this really nice sigmoid-shaped curves here that described how the probability of wave breaking varied in the surf zone. So what the different colors here indicate are different beaches or different locations, and we could correlate that with the beach morphodynamic type. So basically, for more flat beaches, you have a profile that looks more like your first graph here in the A case. And for more steep beaches, you have a profile that looks more like the E panel here. If you want more details about this research in particular, it was published recently in the Journal of Geophysical Research, and you search for the fraction of broken waves, you can get more details on that publication. And the final example here I want to talk a little bit about is about unsupervised deep learning. So the first two examples we had were about supervised problems. So we knew the first example, what the time series were. And the second example, we knew whether the wave was breaking or not. However, most of your data is going to be unlabeled, so it's going to be unsupervised. And there's a very strong push recently on the deep learning community to tackle more and more unsupervised deep learning problems. And one type of problem here is called an autoencoder. And what you have is basically a model that you have. And this example here is an input image, but we're going to see that it could be input time series. Use a neural network to shrink down that information to a thing that's called a latent space. So if we go back in the previous example here, so here you have your input, and what is in the middle here is known as latent space. And from an autoencoder point of view, you shrink down that information from your input image or time series, you shrink down to a bottleneck, and then you expand that information again. So your output is exactly the same as your input. So your neural network is learning how to reproduce your own data. And that's okay because we're not interested in the outputs in this case. In this case, we're interested what's going on in the latent space here, what's going on in the bottleneck. And translating that information to a nearshore example, here we have as input to the neural network, we have a energy density spectrum. So we have the wave spectrum. So we have the time series from the pressure transducer. We obtain the wave spectrum from that time series. We input that in the neural network, in the first layer here. We shrink down that neural network to only two neurons here in the latent space. And then we expand again that neural network to the original input. So what you input in the neural network is exactly what you're getting in the output. So the neural network has to learn how to reproduce, in this case, your wave spectrum. And what we are actually interested in this case is what's happening in the latent space here in the bottleneck. So in this case, I have only two neurons in the neural network. And because it's only two neurons, I can actually plot that in a XY graph, looking scatter plot. And I can label the data from where it came from the locations where it came from. So if you take what's here in the latent space, and we actually zoom into that, we can see hidden structures in the data. So looking at those two neurons in the input space, so we have the first neuron here in the y-axis and the second neuron here in the first neuron in the x-axis and the second neuron in the y-axis, and we cluster that information in the latent space, we can actually infer quite a lot of information from that. In this case, we were interested in the difference between the beach types. So what the neural network actually learned was that more reflective beaches have a spectral energy density peak here that's really long period, so we call that infragravity waves. So they are waves that have period below 25 seconds. On the other hand, in the very opposite corner here in the latent space, we have very steep pitches, and the spectral signature of those locations have a completely different shape, with most of the energy being here in the C-swell frequency, where the periods vary between 1 and 20 seconds. So what the latent space of the neural network was showing in this case was a clustering of different pitches based on the spectral signatures. So it was putting the spectral signatures in completely different locations in the latent space. And that has a physical meaning, has a very well documented difference between those two beach types. And it was quite interesting to actually learn that information only from the data, because we already knew that information was already published in the 80s from Short and Wright. And they defined a model that told you that, but they went to the beaches and they did that visually. So they observed what was happening there and they came up with the conceptual model. What I was able to show here with data only is that we can have the same classification scheme, but only based on data. So the model has, in this case, the model had no knowledge at all what a deceptive or reflective beach, or where 7 Mile Beach is and where Wary Beach is in this case. So it was quite interesting. And just some final considerations here. So that we can adapt AI and machine learning to pressure sensors relatively easily. I showed 3 examples, so time series classification, feature extraction, and data exploration. And this techniques can be fairly easily extended to solve another environmental problem. So if you have, for example, temperature, you have other information like turbidity, you can actually apply these techniques to that data as well. And well, that was all I had for today. Thank you very much. And I think we go to questions now, right?
Thank you, Keo, for this great presentation. Now I don't know if you have a question for you. I have a question about swatch zone, because you plug your sensor on a chain on is a very shallow water on with on a large wave coming inside the sensor. You don't have a problem acquisition for that with a Ensemble model.
No, we never had a problem with swatch zone acquisition. Actually, it's very robust, the data we get from the swatch zone pressure, for the swatch zone sensors. The only problem we have sometimes is that the sand is moving, so the waves are actually shifting the sand, and sometimes the sensor gets buried in the sand, and you get a shift in the pressure because the sensor is actually buried in the sand. So you have to be aware that sometimes your sensor can be buried in sand, and the pressure you're actually seeing from the logger is not the real pressure. The height corresponds to the height of the wave. That was the only problem that we had.
Okay, on other question, it's about the accuracy of your measurement. You are happy with that in very shallow water for your demo, your measurement on the wave?
Yes, yeah, we very happy with the accuracy of the measurement. We sometimes when you deploy it deeper, it gets a little bit harder. So if you go beyond 5 meters, you start to have attenuation with depth, and then we have to plan how you're gonna configure the sensor a little bit more thoroughly. But in the surf zone, in shallow water, and for the waves that we were studying, we never had any problem.
And you use a sampling mode at 2 Hz for that, or bigger?
No, we What I do typically is I sample the highest as I can, either 32 or 16 hertz, depending on the sensor. And then on post-processing, I resample that to 5 hertz or 10 hertz, depending on the location, depending on the time series. But usually I try to record at the highest possible frequency and only resample if I need in the post-processing.
Okay, thanks. Any question?
Maybe I'll have a quick side question, Kyle. For your neural network, and you may have said this at the beginning, do you initialize the weights of the inner layers, or was that fully random?
It was fully random because I had nowhere to initialize it from.
Okay.
So it starts from random weights, and it trains the neural network.
Very good. Very
For
cool.
that example, it's fairly quick, so it takes about only 10 minutes on a standard laptop. It's very quick, fairly quick to train that neural network. The autoencoder that I showed that has the spectrum in the input and the output, that takes a little bit more time because it has a lot more neurons, and the neural networks is more complex.
And what's the distribution? How many layers and how many nodes?
For the first neural network, the wave classification, that is the actual neural network. So this is exactly the neural network I use. So it has the input here is exactly that. So it's 17 variables, if I remember correctly. Then it has 3 hidden layers with 256 layers, neurons per layer, and just 1 output layer here in the end. So this is actually the representation of the neural network. And then for the second one, I shrink it down from, so the input here is a lot larger. So it's 2048 data points. And then I shrink it down to 2 in powers of 2. So it's fairly arbitrary how I chose that, but it starts with 2048 and goes 1024, 512, 256, and so on, all the way down to 2. But that's arbitrary.
Sure. Okay, thank you.
Okay, thank you. If you don't have more question, we have stopped the webinar here. I just stop the recording now. Thanks again to Kayo for your presentation. I hope see you next time for other webinar coming from rbr.